Today we're going to look at graphing rational functions. Our objective is to be able to find the domain, vertical and horizontal asymptotes, and x and y intercepts of a rational function, and to be able to graph a rational function. So what is a rational function? It's a ratio of two polynomials. So we've already dealt with polynomials this year, and we know f of x is our function notation, and our rational function is just a ratio, so a fraction of one polynomial, we'll call it p of x in the numerator, over another polynomial, and we'll call it q of x. And we're going to use these labels, p of x and q of x, the entire chapter. We're also going to be using asymptotes again. We talked about these when we did our exponential curves, and now we're going to do it again this chapter. And if you remember, an asymptote is just a line that a curve approaches as you go to infinity. So this chapter we're going to have vertical and horizontal, and there's actually something called a slant asymptote that I'll briefly talk about this chapter, but we don't deal with it in this class, but your classes in the future will talk about them. We have 5 pieces of information that we're going to use to try to help us sketch a rational function, and the first one is called the domain. And if you remember from before, domain is our input, our x values that we can substitute into our equation to get an output, a y. But we do come across a problem now that we are dealing with a ratio, a fraction. If you remember, if we have an input, that input can never make the denominator 0, because if we divide by 0, we get an undefined value. So it's impossible to have a graph where we have an input that gives us an undefined value. So we don't allow those in a domain, which we call a domain restriction. And when we have a domain restriction, we get something called a vertical asymptote at that x value. We're going to get a dotted line, a vertical dotted line, wherever the x is undefined. We're also going to find horizontal asymptotes, and this page can be a little scary, but it's really easy to find it. What we're going to look at is the degree of the numerator versus the degree of the denominator. And if you remember degree, to find it, we look at the exponents of all of our values. Say 5 minus 2. Let's put an 8 in front of it. If we looked at this one, the degree would be 7. Hopefully you remember that from our polynomial chapter. And we call the 8 a lead coefficient. It's the coefficient, our constant value, in front of our x with the largest exponent. Well, what we're going to do is find the degree of the numerator and the same place the degree of the denominator and make a comparison. If the numerator is larger than the denominator degree, we actually don't get any horizontal asymptote. We actually get something called a slant asymptote, which I'll just briefly talk about later in this chapter. If they are equal, what we're going to do is take the lead coefficient of p of x divided by the lead coefficient of the denominator q of x, and then we're going to get a new ratio. And because it's a horizontal asymptote, it's going to be y equals that number. And if the numerator is smaller or less than the denominator's degree, we will always get a horizontal at y equals 0. And as we go through the 4 examples, you'll get to see how those play out. The last things we're going to look for are the x and y intercepts. And we've done these a lot this year already. And I'm hoping you remember that for every x-intercept, which is written as a point, we're going to set y equal to 0. And for every y-intercept, we're going to set x equal to 0. But you might think, well, there are no y's in this problem. Hopefully remember that y is the same thing as f of x. So in this, for example, we would set f of x equal to 0. So I'm going to get 0 equals p of x over q of x. And our goal is, again, these would be polynomials, is to solve for x. Well, if I make this 0 over 1, now I have a proportion. And to solve a proportion, we usually cross multiply. So 1 times p of x is p of x. 0 times anything is 0. So in essence, to solve for our x-intercepts, we're really just setting the numerator, or p of x, equal to 0 and solving for x. And that's a much easier way to think about it. You could always substitute 0 in for y and cross multiply, but you're always going to end up with the numerator equal to 0. And the biggest mistake I see with y-intercepts is that students forget to set all of the x's equal to 0. They just look at the numerator, they don't look at the denominator for the x's. So remember, anywhere you see an x, you're going to substitute in 0 and then solve for your y, or in this case, f of x. So we're going to go through 4 examples. I'm going to show you how to find the 5 parts and how to use that to actually graph. The first thing we want to look at is the domain. Remember, the domain is all the inputs that work, and it's usually all reals. But we always get we usually, not always, but get some exceptions where, is there ever an x that I can substitute into the denominator and make it 0? Well, remember, we don't want x minus 2 to be equal to 0. Because if we have it equaling 0, we get a 0 in the denominator. So what does that tell me? That means that x cannot be equal to 2. So how we write our domain is all reals, x is not equal to 2. As you get into some other math classes, you might do something called interval notation or set notation. This is all we're going to do right now. All reals, x is not equal to 2 for my class. Which means that I can never have an input of 2 on the x, which means I will never get an output along this vertical line where x equals 2. So that means I'm going to get a vertical asymptote at x equals 2, because I will never be able to put a point anywhere along this line, because this line represents all the inputs of 2. Now we want to find a horizontal asymptote. Remember, that's the degree. I want to look at the degree of the numerator and the degree of the denominator. So if I look at the numerator, the highest exponent for x is 1. If I look at the denominator, the highest exponent is 1. And since they're equal, my horizontal asymptote is just y equals whatever the lead coefficient is. So the imaginary number happens to be a 1. If I look at the denominator, in front of this x to the first is a 1, which means I'm going to get a horizontal asymptote at at y equals 1. So I'm going to go to y equals 1 and put in my dash line. So if you look, the red line is very important. Anytime you have a vertical asymptote, because the domain does not exist here, we use this to break it up into two parts. We have a left side and a right side. Okay? On the left side, we have a top and a bottom. Because all our rational functions are exactly that, they're functions, that means it has to pass the vertical line test, which means I can't draw a graph up here and down here, because then my vertical line would cross it more than once. And remember, an asymptote is where, as we get further, as we go towards infinity, our curve goes towards it. So that means as I go up forever, my graph should get closer and closer to this dotted line. As I move left, it should go closer and closer to this dotted line. So I'm either going to get a curve up here or a curve down here. And likewise on the right side, I have a top and a bottom. It's either going to be on the top or on the bottom, never both. So how do we find those? Well, what we want to do is look for our x-intercepts and y-intercepts to give us some points to start at. If you remember, x-intercept is when we put 0 in for y and solve for x. And I'm just going to do this the first time to show you actually substituting it in. I'm going to put this over 1. If I cross multiply, I get the numerator times 1, which is just the numerator, equal to the denominator times 0, which is just 0. So I'm going to get x equals negative 3. And remember, x-intercepts are a point, so I'm going to write negative 3, 0. So I'm going to put a point on my graph at negative 3, 0. But now I want to find the y-intercept. Remember, the y-intercept is when you put x as 0. So it's every x. So I have 0 plus 3 over 0 minus 2, which is negative 3 halves. Again, write it as a point. I like to keep it as a fraction so it's exact, but that is negative 1.5. So I'm going to go down 1.5 and put a y-intercept. This gives me a good idea, because remember I said my graph is either going to be on the top portion or the bottom portion. There are a few rare instances where it will cross a horizontal asymptote and curve back towards it. It doesn't happen very often. So now I can tell that I'm going to be in this bottom section. As I move farther away from my origin or towards infinity, it's going to get closer towards that asymptote or hug that line. So I'm going to get a branch, is usually what we call it, down here in the bottom left-hand quadrant of my new graph. But now I need to decide is going to be on the top here or on the bottom. You can always substitute in points. You can always make like a little t-chart, have an input of an x, figure out what the y is, or our f of x, and be able to plot points. You should never not be able to graph any function that we give you, because you can always just pick an x, substitute it in, figure out what the y is, plot a point, and keep doing that until you can figure out what the graph looks like. But we actually have some really good clues if it's on the top or the bottom. Remember, I have to hug and go towards these asymptotes. So it's either going to be up here, like this, or down here, like that. But if I have this on the bottom, I'm going to have to at some point cross this x-axis, whether it's right here or way down in the future. But I know this is the only x-intercept that exists, which means that the only place I can touch the x-axis is here. Well, since I'm going to have to eventually hit the x-axis if my curve is in the bottom portion, I know that this is impossible. So it therefore must be up here. Now, how could I prove this to myself? Well, what I could do is take out a calculator. Okay, if I take out this calculator, I could pick an x value, let's say 10, and substitute in. That would give me in the numerator 10 plus 3. In the denominator, it would be 10 minus 2. If I type that in, I get 1.625. Well, if I go to 10 and I go up 1.6, if you notice I'm right around here, which is right where I put my curve. So that will also help you know it's in the top portion, not the bottom portion. Okay. Let's look at our second example. This one now, when I figure out the domain, is going to take a little bit more because now I have not a linear function or a linear polynomial, I have actually a quadratic. And again, if I want to solve and make sure that this denominator is never 0, what I could do is I could make sure that x squared is never 9, which means that x is never going to be a positive or a negative 3. And remember, you have to take the square root, which means it's plus or minus. Now, if you're going to forget the plus or minus, which a lot of students do, another way to think about this is just to take and factor it. X plus 3, x minus 3, and I know that cannot be equal to 0, which means I'm going to get negative 3 and positive 3, just like I did here. But remember, any other number I substitute in works, so it's x is all reals, but it cannot be a positive 3 or a negative 3. Which means that I'm going to get a vertical asymptote at a positive 3 and a negative 3. So I'm going to go to negative 3 and put in my dashed line, and then go to positive 3 and put my dashed line. Okay, now I want to go on to my horizontal asymptote. I'm going to look at the degree of the numerator and of the denominator. Now, there's no x's in the numerator, which means I have a degree of 0. I have x squared, which means I have a degree of 2. Since the denominator is larger, the bottom wins. Remember, that means I'm going to get a horizontal asymptote at y equals 0. So I'm going to put my dashed line right at y equals 0. To find my x-intercepts, remember, you could put in 0 for y, but remember, it's the same thing as setting the numerator equal to 0. But negative 8 doesn't equal 0. This doesn't make sense. Okay? So what does that tell us? The algebra doesn't make sense because what you're trying to do is impossible. And that's because when I ask if there's x-intercepts, you tell me that there are none. So that means I can never, ever, ever touch this x-axis, which means I'm not going to be able to go from the top and cross to the bottom. So I'm either going to be at the top or at the bottom, never going through. Let's find our y-intercepts. Again, I'm going to take my function, anywhere I see an x, I'm going to substitute in a 0. And this is going to give me a negative 8 over a negative 9, which is a positive 8/9. And again, we write it as a point. So if I go 0 and then just below 1. And again, this isn't, obviously it's hard to graph 8/9, but that's why I have you write the information on the left. But now I need to know where I'm going to put my other graphs, or my other points on my graph. So you might just think, okay, well, if I don't know where this goes, I can always do input and output. So is it going to be on the top or on the bottom here? So to do that, I'm going to have to input a number like negative 4, negative 5, 6, 7, 8, 9, 10, something like that. And you can always pick more than one. So let me take my calculator again. In my numerator, I have negative 8, and I always like to use parentheses. In the denominator, let's try substituting in, say, a negative, a negative 6. So I'm going to put negative 6 squared, so again, you want to use parentheses for negative 6, squared minus 9. And if I do that, and close the parentheses, I get a negative number. Okay, so I get a negative 0.29. So if I go to negative 6, 1, 2, 3, 4, 5, 6, I get a negative 0.2. So I know I get a point about there. So now I know I'm in the bottom section. Okay, what about on the right section? Let's try the same thing. Second enter. I'm going to do the same thing, but this time I'm going to put in a positive 6. And this is just the only reason I'm using 6 is because it makes it a lot easier to type it in. Oh, I get the same exact answer, because when you square a positive or square a negative, you get the same value. So I'm going to go to positive 6, 3, 4, 5, 6, and put a negative 0.2. So now I know it's in this bottom section. But what happens in the middle? The middle is always weird, because now I have a left, a center, and a right. The left and the right are usually either on the top or the bottom of our horizontal line, but the middle, it's kind of tricky. Sometimes it's just on the top, sometimes just on the bottom, or sometimes we'll actually get something that kind of looks like our little snake, our cubic, that goes one direction or the other. So how do we do this? Again, I'm going to do, since I have this point, I'm going to do a test point on the left and the right. So let me pick, say, negative 2. So the nice thing about this, if I type it in correctly, I can just go back. I'm going to insert a negative 2. Okay, and if I hit enter, I get a positive 1.6. So I go negative 2, 1.6. So now I know it either curves back up or it would go down. Okay, so let's do the same thing. Let me pick a positive 2. 1.6. This is what many students will have to do to understand where the graph goes. But let me bring up something again like we did in the last one. Remember, I have no x-intercepts, which tells me I can never ever touch this line. So the only option I did have is for it to go down, go through this point, and then curve back up. But again, you should never have to guess. Just substitute it. Use your calculator, substitute it in. It doesn't have to be a graphing calculator. I can give you a non-graphing calculator, because that's usually the portion this is on, and you can type it in and figure out your x and your y. Like, for example, if I put in a 2, I get 1.6, and then I can plot that point. Let's look at example number 3. Again, I want to make sure that my denominator is not equal to 0, so that means that x is not going to be equal to negative 1. So my domain is all reals. X is not equal to negative 1. Okay, and if you can do the math in your head, you don't have to write it out, but just so you know. That means I'm going to get a vertical asymptote at x equals negative 1. So I'm going to put my dashed line here. Again, if I want to find the horizontal asymptote, I look at the degree of the numerator and the denominator. The numerator is x squared, so it's going to be a 2. The denominator is x to the first power. Now here, the top wins, which means I don't actually have a horizontal asymptote, which means I'm really going to have something called a slant asymptote. We don't go through the algebra to find it in this class, which involves using long division, which we've already learned, but you're going to actually see the slant asymptote without us actually graphing it as we go through and plot our points. So now finding our x-intercepts, remember you can just set the numerator equal to 0 and solve for x. So hopefully you know there's a GCF of an x, so I'm going to get x times x plus 4 equals 0, which means x equals 0, or x equals negative 4. So I'm going to get 0, 0 as one x-intercept, negative 4, 0 as the other. And for my y-intercept, again, anywhere you see an x, I'm going to put in a 0, so I get 0 squared plus 4 times 0 over 0 plus 1, which gives me 0 over 1, which, again, 0 in the numerator is okay, which is 0. And hopefully you know by now that if you have an x-intercept of 0, 0, you're always going to have a y-intercept of 0, 0, because they're the exact same point. So, and this is the origin, so it's on both axes. So I get 0, 0, and negative 1, 2, 3, 4, 0. So if you look, this looks a little different, because I don't have that horizontal asymptote. I don't have this other line to hug. So again, I'm going to go back and do the same thing before. I'm going to pick some points, some x's and some y's. Okay, so let's pick, say, negative 2 and see what we get. Because I want to know what happens here. Is it going down or going up? And then let's pick something further away, say negative 10. See what happens when I pick those points. So if I turn on the calculator, I'm going to clear it. In my numerator, I'm going to put in a negative 2. So again, you need lots of parentheses. So I'm going to use a parenthesis for the numerator and then a parenthesis for the negative 2 squared. Oops. 2 quantity squared. Let's see if it picks it up. Okay. Plus 4 times negative 2. That's my numerator, divided by my denominator of negative 2 plus 1. Does not like the 2 today. Negative 2 plus 1. Okay, now I'm going to hit enter, and I get 4. So I know that I'm going to get a point, negative 2, 1, 2, 3, 4. Okay, but let's see what happens further out, because I don't have this horizontal line to go towards. So I'm going to do the same thing, but now I'm just going to insert a 10, and then another negative 10. Okay, and then make sure you remember to plug that, substitute that in for each place. Okay, and then I'm going to hit enter, and I get negative 6 2/3. Okay, so again I'm going to get negative 6, 1, 2, 3, 4, 5, 6, and 2/3. Alright, so I can kind of see it doing this. So let's kind of connect those points. I know here's my asymptote, so it's going to go towards this, but here it's going to curve through and then kind of go like this direction. So let's try again on the other side. So let me pick similar points. Let's try, since I know the points right here, I want to see what happens on the other thing. So let's pick, say, 5 and 10, kind of to see what happens. So I'm going to go to my calculator. Anywhere I had a negative 10, now I'm going to put in a 5. Okay, actually, let's make it a little bit easier. Let's start with the 10 first, because I can just get rid of the negatives. So let's delete that negative and delete that negative. So now I have 10 every place, and now I get a 12.72. Okay, so at 10 I get 12.72, so something way up here. If I do the same thing but insert a 5, okay, I'm going to get 7.5. So, but plot that point at 5, I get 7.5, and now I can kind of graph, see what this is going to do. It's going to kind of come up here and then go towards this. Now, we didn't find what we call the slant asymptote, but if you can kind of see this one, there's kind of this imaginary line that these are going towards that slants and goes towards it. Now, if we did the long division and actually found the equation of this line, we could, but like I said, we're not going to do that in this class. But some that don't have a horizontal asymptote, they kind of veer off and kind of go on this diagonal. Alright, so let's look at one last example. I know this is a little bit longer, but hopefully you have enough examples after this to kind of go through if you struggle a little bit. Now, if you notice here, I made the denominator a little bit longer, but you should hopefully know that this factors to x minus 6, x plus 1. And we want to make sure that does not equal to 0. So that means our domain is going to be all reals, but x cannot be positive 6 or negative 1, which means I'm going to get a vertical at 6 and at negative 1. So again, we have this broken down into 3 parts, the left, the center, and the right. And now if I look at my horizontal, I'm going to get d is equal to 2 for my numerator degree, and the degree of the denominator is 2. So they're equal, which means I'm going to look at the lead coefficients. The lead coefficient of the numerator is 3. The denominator is 1, so now I'm going to get y equals 3 as my horizontal asymptote. Okay. My x-intercepts, I'm going to set the numerator equal to 0 and solve. So I'm going to get 3x squared equals 12, x squared equals 4, which means I'm going to get x is equal to plus or minus 2. So I'm going to get 2, 0, and negative 2, 0. It's okay if you write plus or minus 2 as well. So I'm going to go to 2, 0, and negative 2, 0. And then for my last part, anywhere I see an x, I'm going to substitute in 0. So 0 squared minus 5 times 0 minus 6. The numerator becomes negative 12, the denominator negative 6, so I get a y-intercept at 2, so 0, 2. So I'm going to go 0 up 2. Now I can kind of see what's going on here anyways. Okay, and I'm going to go through this one a little bit quicker, but I'm going to get, and you can always do test points. You'll see where they are. Input and output. That graph's going to go like this. I have to go through these 2 points, so I remember I have to hug the red lines for sure. And then, since I can't curve back and hug this line because it wouldn't pass the vertical line test, I know this is going to come over here. And again, just substitute in a 3, a 4, or 5 to see what happens. Now, does this going to be on the top or the bottom? Well, remember, these are the only 2 places I can cross the x-axis. And if I'm going to hug the lines down here, I would have to cross the x-axis at some value greater than 6. But since that's not possible, I know my last branch is going to be up here. And that's what that last one would look like. I hope you feel a little bit better about graphing rational functions, being able to find the domain, vertical and horizontal asymptotes, x and y intercepts of a rational function, and using that information to come up with a graph.